Right. So so as we said, we're now discussing how to derive bulk properties from kinetics, how to go from the finest scale description, which would be this. This is where we talk about kinetics. Okay. And this is where we talk about bulk properties. Bulk properties such as what? Such as density, average velocity, so on and so forth. How to go from here to here, how to do the coarse graining, and in doing so, we will have to go through what's called the mesoscopic description, which involves distribution functions. Okay, so that's our goal. Consider a gas whose molecules are in thermodynamic equilibrium. They have, now this word means a lot of things, thermodynamic equilibrium. For our purposes, it's sufficient to consider this definition to mean that the collection of molecules has a well-defined temperature, for instance. Okay, that's good enough. It has a definite distribution by virtue of being in thermodynamic equilibrium. It has a definite distribution, which is what characterizes this stage. Okay, the mesoscopic, shall we say, picture. For instance, if it was, a collection of gas molecules with a well-defined temperature, it would be the Maxwell-Boltzmann distribution. Okay, I want to keep this discussion general. I don't want to tie myself exclusively to the Maxwell-Boltzmann distribution, just to sort of alert you to the fact that there can be other distributions, non-thermal distributions are possible, especially in astrophysics. But so I just wanted to, which is why I said, say, for example, a Maxwell-Boltzmann distribution, but not necessarily. But if you would like to proceed with the Maxwell-Boltzmann distribution as a concrete example, that's just fine. Okay, right. So, I don't understand what's going on, sorry. Yeah, right. So, you might ask, what is this distribution function? I mean, how do you define this distribution function f? Well, this is really the definition of the distribution function. You take the distribution function, okay, you integrate it over, let's do this. All space and all velocities, right? So the f, and that gives you the total number of particles. Okay, so this is the definition of the distribution function. F is, of course, by the way, this should be vectors. Okay, so f is a function of space as well as velocity. That's assumption. Okay, so this would be a 6-dimensional integral, 3 dimensions for space and 3 dimensions for velocity. You integrate the distribution function over all space and all velocities and you get the total number. And this is a dimensionless quantity. Number is number. 100 particles. 100 particles in a box measuring this by this by this, right? And with velocities ranging from x-directed velocities ranging from something to something, y-directed velocities ranging from something else to something else, z-directed velocities ranging from something else to something else. Okay, so you carry out the 6-dimensional integration and you get a total number, a dimensionless quantity. This is the definition of the distribution function. Right. Now, if there was an average velocity, okay, then what happens is, so this would be the total number. Now you stick a v in here. This is, I mean, if you think about what you've learned about distribution functions earlier, or what you learned about averages earlier, this is simply the definition of an average. Okay, this is the normalization, and you divide by the normalization out here, instead of having, you can think of this as a v raised to 0 f d cubed x d cubed v. This on the other hand is v raised to 1. So you stick in, so this is the first this is called the first moment. What kind of moment? Well, velocity moment. And the first moment gives you the average, if there is an average. Maybe there's no average. Maybe the room I'm sitting in with these molecules, colliding with each other, the gas molecules colliding with each other, it does not have an average velocity. The air is very still. There's no breeze flowing through this room. So the average velocity is 0, which is why I said average velocity, if any, would be this. Okay, so this would be the 0th moment. This is the if I wanted to find out the average position, instead of the v, I would have an x. And so that would give me the average position, if there exists such a quantity. Okay, so this is how you get moments of a distribution function. This is how you define a distribution function. This is how you get moments of a distribution function. The second moment of velocity would be, well, instead of the v, you have a v squared. Right. And what is the average of v squared? When you just stick in a half m inside the v squared, that's very easy. It doesn't enter the integral, so you just take it out, right? 1 over n of half mv squared. So you get the second moment gives you the average kinetic energy, right there. And average kinetic energy, as you know, is this is what defines the temperature for a Maxwell-Boltzmann distribution. If you plugged in the exponential kind of form that characterizes a Maxwell-Boltzmann distribution, you would find that carrying out this integration will give you 3/2 kT, and I will assign this as a homework problem somewhere. Okay. I would like you to explicitly carry out this integration and show that this is indeed so. It's good to do these things once in a while. It's good to, at least once carry out the integration, verify that this is indeed so. Okay, because with an explicit, Maxwell-Boltzmann distribution function. Okay, so this is just to sort of, carrying out this exercise will reinforce. I don't want to say drive home, but reinforce. I'm sure you already know this, but reinforce the point that the temperature is simply a measure of the kinetic energy of the randomly moving colliding particles. Okay, so therefore, and things like temperature and therefore by extension pressure. If there's no temperature, there's no pressure, right? Zero temperature, zero pressure, right? So things like concepts like the pressure of a gas is thus a macroscopic concept. It arises from the fact that you've carried out this averaging. Averaging over what? Over all space and all velocities. Or, not really all space, not infinite space, but some, all the space that you're interested in, all the molecules in this room or in a large box or so on, so something like that. Okay, therefore, you've averaged over a macroscopic volume, and therefore, a quantity like a temperature or the pressure is thus a macroscopic concept, which represents a statistical average of the force per unit area due to molecules. You know this. You know this. You already know this from your 12th grade physics. This is how it's. This is just a somewhat more detailed way of understanding this statement. Okay. All right. Let's move on. Having understood or at least introduced how these average quantities come about, like number density, temperature, pressure, etc. Let us now talk about conservation quantities, right? How, so in what we talk about, the number density is essentially number per centimeter cubed. And what we will now call rho is mass density, so it would be grams per centimeter cubed. And the way to go between here and there is just multiply the number density by an average mass of the per molecule. Okay, so that's how you go to grams per centimeter cube from number from number per centimeter cube, right? So having oh yeah, also for instance velocity. Okay, so having understood how these average quantities come about, you can this is how one does mass conservation. This essentially is a statement of the fact that mass is neither created nor destroyed. If there's a volume and the mass density inside it is changing, that's only because there's a divergence of the mass flux inside the volume. Either a mass is flowing into the volume or out of the volume, okay, or being created inside here, being truly created inside here. Someone is magically, putting in stuff. Okay, and that is outside the purview of this volume. I am putting in stuff by hand. That's what this says. Okay, so the sum of that and this is always zero, and that's what mass conservation is. This is nothing but momentum conservation. This is F equals ma. This is the ma part of it. Ma for a fluid parcel, and these are the F's. This is the F due to, okay, so these are the two contributions to F. This is the F due to body forces such as gravity. This is the force due to pressure gradients. I've written this as a divergence of a pressure tensor, but if you want to think of it as a scalar pressure, it's just a pressure gradient. The pressure here, you have the pressure here greater than the pressure here, and so fluid flows from a region of higher pressure to lower pressure. That's what this term is saying. This term is simply saying that there can be body forces, there can be forces on an element of fluid due to body forces such as gravity. Okay, so this is simply a statement of F equals ma for a fluid. The new thing, and you're already familiar with F equals ma, of course, for discrete particles. The new thing for a fluid is this out here. Okay, the fact that you have a contribution from the gradient of pressure. In this case, the divergence of a pressure tensor, but that did not, you can still think of it as a gradient of pressure. And so this is what's new when you start thinking of a continuum such as a fluid as opposed to discrete particles. Yeah, or more simply, instead of this, you can also this would be what's called an Eulerian description. This is what's called a Lagrangian description. I don't have too much time to go into this. As I said, I expect you to pick this stuff up from Fluid's books. We can discuss this offline a little bit if some of you are finding trouble with it. But for the time being, let's go on. Okay, now this is for a neutral fluid. Okay, so the only forces that are acting on an element of fluid are gas pressure and body forces, if any. And so this is again written a little more simply like this. Yeah, so if gravity is present in this equation. I've neglected gravity. The main thing I wanted to point out that is the difference between this equation and this equation. Okay, the main thing is this guy, which is what's called the Lorentz force. Okay, and this assumes importance when you're talking about a gas which comprises whose particles, when we're talking gas, of course, you're talking about a macroscopic description in which there are no particles at all. It makes no sense to talk about, but nonetheless, you know that there are particles that comprise the gas. Okay, lots and lots of particles. Therefore, you know, in the gas description, the particles are completely cross-grained over. You don't see the particles anymore. But nonetheless, you know that there are particles in there. Okay, now if those particles are charged, they will respond profoundly to electric and magnetic fields. Okay, and this is the term that tells you how. This is the term that tells you how the presence of a magnetic field in a current carrying fluid manifests itself. So this is an additional component of force. This is a force. There's also a force. In a charged fluid, there's an additional component of force, which is called the Lorentz force. It's essentially, your Q V cross B that you're very familiar with. It's really the same thing if you think about it. It's a QV is really J, and this C is the C comes about because I'm writing this in CGS units. This whole thing is written in CGS units, and that's why the C comes about. If you were writing it in SI units, then you would write it slightly differently. You would not see the presence of the velocity of light. Okay, and I tend to work in CGS units, astrophysicist, but I'll try to be a little more, a little unit agnostic. I will also, anyhow, we will see all this as we go along. So, as of now, I'm not motivating any of these laws in any detail. I'm simply writing them down, discussing them a little bit, and leaving them at that, because when we do magnetohydrodynamics, we will be talking about these things in much more detail than we have done now. I simply want to point out that just before we leave this, I simply want to point out that for a fluid that comprises charged particles, you can loosely call it a charged fluid, but that's not really accurate, because macroscopically, the fluid is neutral or quasi-neutral. The fluid as such does not carry any net charge. Okay, therefore it's not really right to call it a charged fluid. It's really a fluid that's electrically neutral, but nonetheless it comprises charged particles. Okay, and when subjected to a magnetic field, it's subjected to Lorentz forces, and so you have an additional term, an additional force term in the momentum equation. Right. So that was when we that was our discussion of the average properties. Okay. Now we will get down. Now we will talk about. We will talk about this stuff some more when we start talking about magnetohydrodynamics. Let us now come back and come back to this description. Well, we will leapfrog between this description and this description. Between the microscopic, the kinetic description, and the mesoscopic description, we will go back and forth these a little bit. But for the time being, right now, we are talking about the microscopic description, okay? Which is why I've termed this slide particle properties of an ionized plasma. What do I mean by an ionized plasma? You have a positive charge and a negative charge. In other words, it's not, for instance, think of hydrogen. It's not neutral hydrogen. It's an electron and a proton. Okay, and for the entirety of this course, it's just fine if you think just of an electron-proton plasma. That's good enough. That can be the prototypical example you have at the back of your mind. Okay. Now, what are the kinds of collisions? So these are the things that we will be discussing soon. The collisions are not simply hard sphere collisions, of course, as we discussed. They can be, there can be Coulomb collisions, because that's the fundamental force between charged particles, the Coulomb force. So the manner in which charged particles interact with each other is via Coulomb collisions. And also, there are these things called screening effects, and we will discuss something called Debye shielding. For instance, if you have a massive positive charge, if you have a proton sitting here and lots of mobile electrons, the electrons will, I've said this earlier, the electrons will quickly gather around the positive charge and screen out the charge. So if you're very far away here, if you're observing, you will not see the entire potential, the entire electrostatic potential of this. You will only see a screen potential, and this is called, and this phenomenon is called, this kind of shielding that these negative charges provide is what's called Debye shielding. We'll talk about this, and what we will discuss what are the all-important collective effects in a plasma. Even though we're talking about particle properties, it turns out that the ensemble of particle properties lead to what are called, the ensemble of particle properties leads the plasma to behave as a collection of particles, even though we are still not talking about the fluid description. I mean, the collective effects in a plasma manifest itself. So we will talk about that also. So this discussion of Debye, we will start with a discussion of screening, and this description of Debye shielding comes from Boyd and Sanderson. Wherever I write B and S, this is Boyd and Sanderson. So okay, so look up the discussion of Debye shielding from Boyd and Sanderson. That's what we're following. So as we've said, a plasma is ionized, but on the whole, in other words, over macroscopic length scales or volumes, it's electrically neutral. Now, the big question is, what are the scales, or rather length scales, that's what I really meant, length scales, over which electrical neutrality is valid? Okay, ask yourself that question. And one would think that the Coulomb influence of a charge in a plasma would extend to infinity, but does it? I've already given you the answer, not really. Okay, so think of a small overdensity in protons. I mean, say you've got protons and electrons nicely sitting in some kind of equilibrium, and for some reason you bring a few excess protons, a small overdensity of protons. Okay, what will happen is a cloud of electrons would immediately rush in to neutralize its influence. Why only electrons? Because electrons being very light, much lighter, 1,000, 2,000 times lighter in fact than a proton, are very mobile. They're not sluggish like the protons. Okay, so it's the electrons which will rush in to neutralize the positive charge caused by the overdensity in protons. Okay, now the density of this cloud would be, the usual Boltzmann distribution, with phi being the electrostatic potential. It would be Ne times exponential of E phi over kTe. Okay, but we know that in electrostatics, the electrostatic potential, this is simply divergence of E is equal to rho over epsilon. Okay, and the E being given by, like that. If you do that, you apply the divergence operator once more here, and you get the Laplacian right there. Okay, and so this is not Laplace's equation. This is a Laplacian operator, and because you've got a something on the right side, it's not zero. This is the Poisson equation. So you've got a source term here, right? And if you write this down in cylindrical coordinates, if you write this, or is it spherical coordinates? I forget what it is. Yeah, that's right. So this is simply in spherical coordinates. That's all this is. This is just the del square operator in spherical coordinates. And if you write this down you substitute for this on the right hand side, and you make a series expansion, and you essentially Taylor expand the exponential and only keep the leading term, you can roughly write this. I mean, this is approximately equal to NE square over, like that. Okay, I leave you to work out the algebra. Okay, and the approximation is because the electrostatic potential tends to 0 as r tends to infinity, so the argument of the exponential, so this argument is small. After all, you can Taylor expand the argument only if the argument is small, right? So as r tends to infinity, as you go to very large r, this goes down to 0. Okay, and so that's the large radius argument. You also have to match, I mean, so you have to, the boundary conditions have to, you need two boundary conditions because there are two special derivatives here. So, so that would be the large radius boundary condition, and the small radius boundary condition, you need to match it. And it turns out that this entire thing in front of phi has the dimensions of inverse length squared, and this is what we call the Debye length, or rather Debye length squared. Okay, so it turns out that if you match the behavior as r tends to 0 with, this is the behavior as r tends to infinity, but you also have to match the behavior as r tends to 0, which would be the usual Coulomb potential. Okay, turns out that, you see, you have phi is this 1 over r behavior. This is the usual Coulomb behavior, 1 over r. Okay, on top of that, you've got an exponential killing term. Okay, an exponential which kills it, which kills this 1 over r behavior. Okay, and so we will discuss this in some more detail when we meet.